Welcome to the class. In the last class, we talked about how we are going to calculate criticality calculation using one group reactor theory. And you know that in one group reactor theory, we assume that all the neutrons are thermal neutrons. But in a practical terms, this is not actually true. Because in some we have some fast neutrons and we can have some thermal neutrons. So here we are going to look at the practical approach to reactor design, which is using two-group diffusion theory to model criticality calculation. But before we start, we have to look for some certain things. We assume there are some assumptions that we are going to make in this thing. That is, first assumption in two-group theory. First, the absorption cross section in fast group is negligible. That's the first assumption. Second, neutrons scattered from fast group to thermal group. That's the second assumption there. Third, all diffusion neutron, or let me put in the neutron produced as a result of fission are fast neutron. This three assumption is very, very essential. First, we assume that there is no absorption cross section for fast group. We only have a scattering cross section because it will scatter down to group 2. The neutron that scatter from the fast group towards the thermal group. And the third one, the neutron produced as a result of fission are what? Are fast neutron. Now, let's look at it as we have, let's just take an example. That we have a neutron. We have a thermal neutron, and this thermal neutron is being thermalized. And when it's thermalized, it is absorbed. You know, we assume that this is a thermal neutron, that he absorbed this. If he absorbed this one, definitely we know that it's going to produce fission. Because this one is not actually, is a total of the moderator and the fuel. So we can put this one at F. This one's supposed to be EA of fuel FT. Because it's the absorption of the fuel that we call fission. But we can use thermal utilization factor to put in F EA phi T. Let's also assume that although there will be some fast neutron that can cause fission. So we added fast neutron correction factor to which is EF EA phi T. Okay? Now, the average number of neutrons that will be produced per fission. If you add it to it, we now have it to be IT EA phi T. This is the amount of fission neutron produced. I know that this amount of fission neutron produced, there will be a fast neutron because though they are produced by the thermal neutron, but the fission is produced by the thermal neutron. But when the fission neutron come out, there will be what? A fast neutron. they are going to be thermalized again to come and cause another fission. Are you getting me? They are going to be thermalized again to come and cause another fission. So this is the number. So the number of fast neutron, the number of fast neutron is equal to T E A by T. If you can see this thing, this is the number of fast neutron that is produced. If you look at the four-factor formula that we written in the last class, which is a K infinite is equal to so we can write this one like this: K infinity over resonance escape probability EA by T. So this is the number of fast neutron that is produced. Now, so the number of fast neutron, we have put it like this. Let's just put it here, which is equal to K infinity over P EA by T is number of fast neutron. Okay, let's now return back to our normal diffusion equation. For the first group, we can write it as D1, group 1, but we say there is no absorption in first group, so there is no absorption. But there is a scattering down minus E1 to 2. But this E1 to 2, I'll just write it as E1. But what is the source? What is the total number of fast neutron that we have? The source that is producing neutron. This is the number of fast neutron that we have. The number of fast, this is the source. The source, the number of fast neutron that you are producing is this. So plus K infinity over P EA phi 2. No, my phi 2 is thermal neutron. My phi 2 is what? Thermal neutron. So let me just put it like phi T. So know that it's a thermal neutron. Now let me write the second diffusion for the second group will be D2 phi 2. There will be an absorption, which is EA phi 2. What is the source of, this? So we are trying to look for the source of the thermal neutron. If you assume that nothing is leaking out, that means all the neutron produced, the amount of neutron that will come to the thermal are the one that is scattered from the first group to thermal group. That's the amount of neutron that will be available in the thermal group. But if you assume that there is a resonance material, that means some will be caught up at the resonance region that will not be able to be accounted for. So the source of the thermal group will be the one that is scattered down to the thermal group. But we have to put it to consider that some of them will be trapped at the resonance region. So we now have it to be plus P scattered phi 1. This is the scattering, the one that scattered from group 1 to group 2. We just use this probability to put the resonance probability, resonance escape probability. So this one will be equation. So this is the diffusion equation for the first group. This is the diffusion equation for the thermal group. Now, what we are going to do now is we are going to solve this thing. But there is only one thing to know, that in the reactor, both fast and thermal group will always behave the same way. But they will have different magnitude. But they will behave, that is, where you have the maximum for the thermal neutron is where you are going to have the maximum for the fast neutron. But they will have different magnitude. Okay? So we can actually say, let the first neutron, which is pi 1, let it be ax. This one denote the distribution, but this one is one that we are going to use for the magnitude. Let's call this one a1. Phi 2, let's say a2x. You can see that both of them will have the same distribution but different magnitude. And let us say we know this one before. So let's call this one equation 1, equation 2. So now let's call this one equation 3, equation 4, and equation 5. That means from equation 5 you can have 5 squared is equal to minus, let's call this one equation 6. Let's substitute equation 6, 3, and 4 into equation 1 and 2. So we have minus d, 1, b squared, a1x, minus e1, a1x, plus k infinity p, a2x is equal to 0, and this one minus d2 b squared a2x minus a2x plus p e1 a1x is equal to 0. If you have this, we can walk through. Let me rub this thing up. We can, all these x can go, they are the same thing. So we now have minus d1 b squared a1 minus e1 a1 plus k infinity p a2 equal to 0, and minus d2 b squared a2 minus a2 plus p e1 a1 is equal to 0. So we can put the like signs together. This one will be minus d1 b squared minus e1 a1 plus k infinity p a2 is equal to 0, and this one will be minus d2 b squared minus a2 plus p e1 a1 is equal to 0. Now we have this thing. So let's call this one equation 7, equation 8, equation 9, equation 10. You know, we can put this one in a matrix form. Let's try and put this one, we can rewrite them. This one we can rewrite them as this one. I want the A1 to become here. This one we can have the P E1 A1 minus D2 B squared minus EA A2 is equal to 0. I just take this one to this side so that I will have A1 here, A1 here, A2 here, A2 here. So I can put this one 10A. I can put equation 9 and 10A in matrix form. And what will I have? I will have minus d1 b squared. I think the opposite will be plus, yeah, because there is minus, plus e1. This one will be p e1. That will be k infinity p ea d2 b squared minus ea a1 a2 is equal to 0. For non-trivial solution, I can assume if this thing, they are not going to be 0, that means this thing is 0, the determinant. Am I right? So that's minus d1 b squared plus e1 p e1 k infinity over p ea d2 b squared minus ea is equal to 0. Because this one can never be equal to 0, so this one will be equal to 0. So I can calculate my this one will have negative also because it has been there, both of them. So this one will give me b squared plus e1 d2 b squared plus ea, p will have cancelled p, minus k infinity e1 is equal to 0. And this one can go to now be d1 b squared plus e1 d2 b squared plus e2 ea is equal to k infinity ea e1. And I can write them in a simple way, which is k infinity ea e1 over d1 b squared plus e1 d2 b squared plus ea. Let's call this one, we have called equation 11, equation 12. Let's call this one equation 13. Let's divide equation 13 by ea e1. Divide 13 by ea e1. This one will go in the numerator. Now be k infinity over, since it's not cross, so we divide it on by e1, divide it on by ea. Now be d1 b squared over e1 plus e1 over e1 d2 b squared plus ea over ea. We know that d1 over e1 is, let's just pick something like k infinity over, you know that d2 over e2 will give you lt squared. Yes. The equivalent is that d1 over e1, we call it, this one we call it diffusion area, lt squared. d1 over we call it fast age, neutron age. So this one is called tau. So we now have tau b squared plus 1 bracket d2 e2 will give you lt squared b squared plus 1. which is equal to what? 1. This is equal to 14. This is what we call two-group critical diffusion equation. It's called what? Two-group critical diffusion equation. The next class, we talk about it.